Hello, this is Mrs. Taylor, and I am going to explain to you how to apply Newton's law of cooling. Newton's law of cooling states that the rate of change in the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. So, the idea here is that we still have a proportional relationship, but instead of the rate of change being equal to k times y, instead of just a k value, it's now a difference. And so when I apply this law, I can find how much time it'll take for an object to cool or to heat up to a certain degree measure, as well as other things. So in this example, this is out of your textbook, it says, let y represent the temperature in degrees Fahrenheit of an object in a room whose temperature is kept at a constant 60 degrees. If the object cools from 100 to 90 degrees in 10 minutes, how much longer will it take for its temperature to decrease to 80 degrees? Okay, so let's make a list of the information we have here. It says that our room temperature is 60 degrees, so I want to note that, and that will be our surrounding medium, the room temperature. So room temperature is 60 degrees. And then it says that the object cools from 100 to 90 degrees in 10 minutes. So it cools from 100 degrees to 90 degrees in 10 minutes. Okay, and then how much longer will it take for its temperature to decrease to 80 degrees? So how much longer would be time will it take for it to cool to 80 degrees? Okay, so that's the information we have, and they tell us that, or Newton's law tells us that our rate of change is proportional to the difference between the object's temperature and the surrounding medium. So according to Newton, our rate of change, which would be dy over dt, is proportional to, the difference between the object's temperature, which we're going to call y, and the surrounding medium, which is 60 degrees in this case. And so this represents our change in temperature of the object. Y represents the current temperature of the object, so the object's temperature. And then this 60 degrees is our surrounding medium. Alright, so if the relationship is proportional, we still have a constant of proportionality. So earlier I was telling you that instead of it equaling ky, it's going to equal a difference. But that k still represents the fact that the relationship is proportional. It's like that scale factor I was talking about in class. And Newton will have to forgive me, but I think we're going to need more space for this problem. So I'll get rid of him. So it says we want to know how long it will take for its temperature to decrease to 80 degrees. So I need to come up with a model for this situation. And so I want to solve my differential equation here to get my model of exponential growth or decay. And so if I use the separation of variables process, I move everything that involves y to the left, move my dt to the right, and I end up with something that looks like this. 1 over y minus 60 dy equals k dt. And then when I integrate both sides, that's how you solve a differential, you have natural log of the absolute value of y minus 60 equals k times t plus c, some constant. Raising both sides as an exponent of e, the natural log would eliminate, and I'd be able to drop these absolute value bars. So y minus 60 equals e to the kt plus c, and we know that this c moves to in front of the e, and if I add 60 to both sides, I have y equals c times e to the kt plus 60. And so that is the beginning of my model, but I also need to solve for some variables, which is why they gave us this initial information. So when time is 0, our object's temperature is 100 because it cools from 100 to 90 in 10 minutes. So if our object's temperature, which is y, is 100, and our time is 0, which would turn this into e to the 0, which would become 1, so that would be c plus 60, and then that means c would equal 40. And so I want to now update my model, my equation here, to reflect that information I just found. And so I would have y equals, instead of c, I'd have 40 e to the kt plus 60. And then I also want to use some of this initial information to continue to find some other variables, my k in particular. And so I know that when it cools to 90 degrees, 10 minutes have passed. So I can plug 90 in for y, 10 in for t, and solve for k. And that would look like this. 90 equals 40 times e to the k, and now t equals 10. And then to solve for k, I would subtract 60, divide by 4. And so that would give me 90 minus 60, which is 30, divided by 4. And I just realized that I should have put in 40 here instead of 4. Knew something was off, so 40 e to the kt. So, excuse me, you don't divide by 4, you divide by 40. So that would be 30 over 40, which is 3/4. Raise both sides, or excuse me, take natural log of both sides to get rid of that e. And so that would be natural log of 3/4 equals 10 times k, and then divide by 10. So k equals the natural log of 3/4 divided by 10. Now I have a c value and a k value, so now I have a model for my scenario here. So instead of k, I'd write, and it's getting very, very involved, but it would be 40 times e to the natural log of 3/4 divided by 10 times t plus 60. And the whole reason for doing that is now I have a model, so whatever time I have to put in, I can get a temperature. And if I have a specific temperature, like in this case, I can plug that in and find the time. So that would be 80 equals 40 times e to the natural log of 3/4 over 10 times t plus 60. And then I would solve. Subtract 60 from both sides. That would give me 20. Divide by 40. That would give me 1/2. And then I would take natural log of both sides. And so I would have natural log of 1/2 equals natural log of 3/4 over 10 times t. And then divide both sides by natural log of 3/4 over 10. And so an unsimplified answer would look like this. Now, on an AP exam that's multiple choice, Of course, they wouldn't have it like this. They would have simplified. The 10 would be moved to the top. And they would expect you to recognize that the natural log of 1 is 0. And so when you expand natural log of 1/2, you actually get natural log of 1 minus natural log of 2. And so the natural log of 1 would become 0. And so this would actually be negative 10 times the natural log of 2. So simplified, it looks like that. And then of course you could just put it in your calculator like this. Either way, you need to include units, which would be minutes. And so that is how you would apply Newton's law of cooling to solve this problem, and also how you would apply integration by representing your proportional relationship here as a differential and then integrating to get your model for that exponential. In this case, it would be exponential decay because the temperature would be decreasing.